So in last lecture we discussed about addressing modes. So 4 addressing modes we have discussed, and we have to discuss index addressing mode. But before coming to the index addressing mode, we will discuss about jump instruction, because these are jump instruction and addressing modes. These things are required to just start writing first program, first relevant program. So now today we will discuss about jump instruction. As already I told you that microcontroller or a microprocessor is a sequential machine. The meaning of sequential machine is that it executes the instruction one after another in a sequence. But at certain point of time, suppose we want to change the sequence of the execution of the instruction, then how to do that? For that, for particular purpose, we are having jump instruction. Just we will see one example. Suppose we are having our first code at memory location 0000H. Here we are having some instruction. Okay, there is one instruction. Now at 0003H there is another instruction. Like this we are having the sequence of the instruction. In this way there are many instructions. So what our controller will do, first it will execute the instruction which is loaded at location 0000H. Then it will come to the next instruction, then it will come to the next instruction. In this way, in a sequence it will execute. Now let us assume that we are having an application, and in that application we want to skip these instructions. We want that our controller should execute this instruction, then this instruction up to this. And suppose this instruction is at memory location 0007H. Let us assume this particular instruction is stored here is at memory location 0007. Now after that, these many instructions we don't want our controller should execute. Controller should execute after this, it should execute this particular instruction suppose 0013H. At this we are having this instruction. So these many instructions we want to skip. So how we should do this? For this we are having jump instruction for our microcontroller and microprocessor. So basically this jump instruction is divided in two types. One is long jump, another is short jump. Now this long jump instruction is a 3-byte instruction. This is a 3-byte instruction. Whereas short jump is a 2-byte instruction. This is a 2-byte instruction. So if we will use short jump in place of long jump, then we can save 1 byte of our code memory, because ultimately whatever instructions we are writing here, these instructions are to be loaded in code memory. That is wrong. And we know the capacity of the ROM in a controller is fixed. For example, in case of 8051 microcontroller, it is 4 KB. And in case of 8052 microcontroller, it is 8 KB. So these are code memory. That okay, ROM. So these are fixed, these are inbuilt code memory. So it is better to write a program which consume less number of bytes. So if we will go for short jump, we can save 1 byte, and in case of long jump, it is a 3 byte instruction. But obviously, if we are saving something here, 1 byte, then we are saving this on certain cost, right? That we will discuss afterward. So this long jump is a 3 byte instruction, short jump is a 2 byte instruction. The example of long jump is, there is in fact only one long jump instruction, and that is LJMP, long jump. LJMP is the mnemonic for long jump instruction, and after LJump we have to mention address. Where exactly we want to send the sequence of our program, so that address we have to mention. And in case of short jump, this is a 2 byte instruction. Again the short jump, okay, we will come to the short jump afterward. First we will discuss just long jump. Now the long jump and address. Here there are 2 bytes reserved for address and 1 byte for the opcode of LJump. So for the LJump, 1 byte for opcode and 2 bytes for address. Now if we are having 2 bytes for address, this means we are having now 16 bits to define the address. So if we are having 16 bits to define the address, then with the 16 bit we can give the addresses to 64 KB memory, right? If you remember, 16 bits means 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. These are 16 bit, and the last 16 bit combination, highest value will be 1111 1111. So with the 16 bit we can give the addresses in between 0 0 0 0 in hexadecimal and FFFFH in this range, and this is your 64 KB. So with the long jump we can shift the sequence of program anywhere in 64 KB memory map. Anywhere we can shift the sequence of the program. But in case of short jump, that limitation, that flexibility we are not having. So that we will discuss afterward. So just to conclude here, LJump is a 3 byte instruction. 1 byte is reserved for the opcode LJump and 2 bytes are for addresses. For example, in this particular case, at this particular point, whenever our controller comes to this particular instruction which is loaded at 0007H. From here I want to transfer the sequence of my program to 0013. So here I will write instruction LJump. And with the LJump, where I want to transfer the sequence of our program? 0013H at this particular location. So now what will happen? We know how exactly controller execute an instruction. What will happen first? The address of your first byte is loaded in PC, that is program counter. It is 0000H. So your controller will fetch the code from 000H code memory and it will execute the instruction. After the execution, PC will be automatically incremented and it will come to the next instruction, and next instruction is loaded at 0003H. So now the PC value will become 0003H. So now controller will execute the instruction from this memory location and it will execute the instruction. It will fetch the instruction from this memory location, then it will decode it, then execute it. So one by one PC will increase, and at one point of time PC will come at this particular location. So now the value of PC is 0007H. So now PC value is this, so your controller will fetch the instruction from code memory 0007H. At 0007H, the opcode of L jump is stored. The opcode of L jump is stored at 0007H. Now at the next memory location 0008H, at this location the 8 lower bits of the address where we want to skip, that will be loaded. So at 0008H, 13H, this value is loaded. At the next location 0009H, at this location the higher 8 bit of the address, this is loaded. So here we are having 00H. So now when PC will execute the opcode ljump, which is at 0007, then it will save, then it will go to the next memory location. Next memory location is 0008H. So whatever is stored at 0008H, that is 31, it will store this 31 in some temporary register inside the controller. And then it will go to the next location 0009H. So at 0009H, higher 8 bits of that address where we want to transfer the sequence, that is loaded. So here it is 00H. So this value will again fetched by the controller and it will be stored inside the controller in some temporary register. And then the value of PC will become 000AH. So 000AH. This is the address of your this instruction which we want to skip. We don't want to execute this instruction which is at location 000AH. So now what will happen? Already 13 and 00 is already stored inside the microcontroller in some temporary register. When the value of PC will become 000AH, then before the execution of this particular instruction which is at this location, this value 0013, it will be loaded in PC. So now the PC value will immediately change. It will change from this to 0013H. This will become the value of program counter. So now since the PC is 0013, that's why the controller will execute instruction from this location 0013. In this way, controller will skip the execution of all of these instructions between 000A to 0012H. Between these locations, all the instructions controller will execute or will skip, and it will execute the instruction which is loaded at 0013H. So in this way we can skip the instructions. Now one point here is when we are writing some code, then it is difficult to calculate what is the memory location where we want to transfer the sequence of our program. So that is why it is difficult, because you have to calculate how many byte instruction is this, how many bytes are there for this instruction, So ultimately you have to calculate all these things, then you have to write this address where exactly you want to transfer the sequence. But here there is one facility given to the programmer, and the facility is, in place of just writing this address, we can write the label also. So here, if I write here ljump ahead, AHEAD. So this ahead is our label, is a label. So whenever we are using any label, we can use any combination of alphabet or digits or some special characters like underscore. But these identifiers should not be from the mnemonics, from our instructions. Right? So when we write any label here, and same label we have to write here, AHEAD and colon. So now what will happen? We have to write this program. After that, when we assemble this program, then automatically assembler will calculate the address of this ahead. It will calculate this address and it will place it here after ljump. So while writing a program, there is no need to write the address, only we can write the label here, and same label we mention here. So wherever same label, assembler will find the same label here, then automatically it will calculate this address, and it will replace this label by the address during the list file. You can find, if you have written any label in the list file, you will find with ljump there are 2 bytes of this address. You can find that. So in this way we can transfer the sequence of our program. So in this particular example, we are transferring the sequence of the program just ahead of the current program counter. But we can also transfer this sequence to the back side. For example, in place of this, if I change this label back and I write here back colon. So now when controller will execute ljump, then it will go to this label back. Back is here. So it will jump back side. And previously it was jumping forward side. So with this ljump, we can transfer this sequence of the program anywhere in 64 KB memory map. Anywhere, because we are using with ljump with 16-bit number. With the 16-bit number, we can transfer the sequence anywhere in the 64 KB memory map. So this is the advantage of ljump, that anywhere we can transfer the sequence of our program. But yes, of course, with ljump, we require one additional byte, which we can save by using short jump. So in next lecture we will discuss about short jump.